Hi everyone, can you please confirm if I'm audible? Okay, so I hope I'm audible. Can you quickly confirm me? I'm audible and visible, right? Cool. So today we are going to start, like this will be just a revision session. So we are going to revise multi-level paging, right? Okay. Let me just start with the introduction with multi-level paging. And before that, if someone is very new, then let me just introduce myself. I'm Sachin, and I'm co-founder and instructor at GoClasses. I have done my masters from IISc Bangalore, and after IISc, I have worked at Amazon as an applied scientist. I've also got GATE All India Rank 33, right, in computer science branch, obviously. Okay, so with this introduction, let me just start today's session. Let me know if everything is fine. Okay, Rahul is saying, sir, please take these sessions consistently, totally depending on these sessions for the revision. Yes, definitely. Sorry, this is Ratul. So, yes, Ratul, I see that your comments are, your comments on almost every video, and these are very valuable to us. So, yes, we will be taking the classes continuously, only just like sometimes if there is some problem, that is why we are not able to take class, but mostly we will be taking classes continuously. Okay. So we will be following the schedule that is already shared with you. If you want, I can share again in the comment section. Okay, let's just continue. So maybe I can give you some brief about the virtual memory and logical memory. Okay, so what is virtual memory and what is logical memory? Right? Can anyone tell me the difference between the virtual memory and logical memory? Let me just start with the difference between virtual memory and logical memory. Right? So can anyone brief me? Like, what do we call virtual memory and what do we call logical memory? If you can tell me in the brief, then that is fine. So what is the difference between these two? We use these two words quite interchangeably, but yeah, there might be some difference, and I think there must be some difference. That's why people use these two terms. Otherwise, we should be just using one term, right? Let me know. So Shiva is asking, will videos come for all the subjects on YouTube? Yes, there will be revision sessions. So it will not be the complete theoretical part. As you know, like we will be just revising most of the things. So yes, it will come, but it will not be in the very much theoretical way. Okay. So okay, I have not received any answer. The difference between virtual memory and logical memory. Let me just probably continue. So let me just tell you what is the difference between virtual memory and logical memory. So let's just start with the logical memory. What is logical memory, right? So logical memory is basically, as the name suggests, it is something logical, which means that it sounds very logical to say that this is the memory. Which means whenever, like as you might know that two phases mainly. One is compile time and one is runtime. So whenever you're compiling, right? Let's suppose this is the compile time phase, compile, and then let's suppose this is runtime, running the program, right? So let's suppose these are the two phases. Now whenever you are compiling, at that time your compiler do not know that this compiler is going to give you a.out that you are going to load, right? The loader is going to load. Can anyone tell me which kind of loader it is? Short term loader, medium term loader, long term loader, something like that, right? So that loader is going to short term scheduler, short term, medium term, or the long term scheduler. So this loader is going to run this program in the main memory, which means it is going to load the program in the main memory. So the running of the program happens after the compilation, since there are two phases, right? Which means, let's suppose you are compiling, maybe you are running it after 1 year, or maybe after 5 years, maybe after 10 years, or maybe after 2 minutes, right? So it could be after 10 years, it could be after 10 seconds also. Whenever you are compiling, after that you may run your program at after any amount of time, right? Maybe after 10 years, maybe after 10 seconds. It is independent of the compilation. That's what I want to convey. Now at the time of compiling, your program, your program has to be compiled. So at that time, that compiler is not aware that where you are going to load after 10 years, right? Nobody knows the future. Is this understood to everyone? Right? It is very hard for the compiler or for anyone the superhuman to predict that what's going to happen after 10 years. Maybe after 10 years you may load your program in the memory which is something like this. This is your actual physical memory, right? And maybe after 10 years you are going to load your program maybe here, right? You do not know what is the start address, what is the end address, or maybe you are going to load your program in the different pages, or maybe different segments, or maybe you are going to divide, maybe you are not going to divide. You do not know that how you are going to run. So this compilation phase should be logically I'm saying it should be independent of what's going to happen at the runtime, right? So the conclusion is that this compilation should be independent of the runtime. So let me write it here. The compilation that you are doing should be independent of what's going to happen on the runtime. Any million number of things can happen at the runtime, which means a million number of things means, so let me just write it, any maybe million possibilities at runtime. Which means you can say at runtime it might be you might be using the paging, right? You might be dividing your program into different pages, right? You might divide the program, you might not divide, you might choose to store some part of program in the hard disk, some part of program in hard disk, and other part in main memory, right? You might choose to say that okay, this part I should be bringing in the main memory, this part should be in the hard disk, something like this. So basically any million number of things you can do at the runtime. So the conclusion is that compilation should be independent of runtime, and that's where this logical memory comes in the picture. We say to the compiler, right? What we are saying to the compiler, that so we say to the compiler that let's not worry about the runtime, okay? We say that okay, let's not worry about what will happen at runtime. What will happen at runtime? We say that you just be happy, which means that you don't worry about what's going to happen at the runtime. Is my voice clear or there is some disturbance? Can you quickly confirm? The reason being is that there is some construction work that is going on top of my floor. Another apartment, so there might be some disturbance. So that's why I just want to confirm. Okay. So what we say to the compiler, that you do not need to worry about the runtime. You just be happy and you enjoy your life, and you just assume. Okay. We are going to say that you just assume logically, right? Logically, your program, the program that you are going to compile, you are compiling currently, logically the program that you are compiling currently will follow a structure, which means we say that the structure that I am talking about is on the next page. So we say that okay, logically you just assume that your program is going to follow certain structure. And what is that structure? We say that see, you just assume that your program is going to follow this, which means it will in the main memory. Okay, the whole main memory is just for your program. First of all, we say this, that whole main memory is just used by your program only, nobody else is using the main memory. At the runtime it will happen. Okay, so it is just a trick that we play with the compiler. We just say that logically you assume that at the runtime nobody else, absolutely nobody, you and only you are going to run in the main memory, and obviously operating system will be there. And then apart from that, in this whole main memory, you are only going to there. you will run your program in the entire main memory. That will start from, let's suppose if this address is 000, something like this, and then this is FFFF. I'm writing in the hexadecimal. If you want, I can write 0x also in front, right? So we say to the compiler that logically you assume your program will follow this kind of a structure, maybe code data, right? Code data. So that's the trick that we play with the compiler, stack and heap, something like this, right? Is this okay to everyone? This is called logical memory, which means this is just logically we are saying to the compiler. Okay. Okay. There is some disturbance, right? Is this better now? Let me just check if I can do something. Okay. Okay. I think this is okay, right? There is some construction that is going on. Maybe that is why this noise is coming. But I'm trying my best to avoid it. Okay. So I hope that is okay to everyone, that what we are saying to the compiler, and that's called relocatable code, which means relocatable code, which means whatever compiler is going to generate. So after the compiler there will be assembler, right? I mean, compiler is going to write some address. So let's suppose that compiler is going to say, compiler will give us the assembly code and assembler will convert it to the binary code. But let's suppose the compiler is going to say that load maybe R1 comma, that is some memory location, let's suppose 5000, right? Then what does this mean to say? Compiler is saying that from this 5000 memory location load to R1. This is what compiler is saying. But can compiler know that okay, it should be loading from 5000? I mean, since the compiler do not know that where are your variables going to store in the after the 10 years, right? After the 10 years your variables, I mean, you may run your program in any million number of ways. So compiler just assume that logically there is some memory that is having operating system, and then 5000 address is, let's suppose, here. Then you load from this 5000, but that may not be the physical, may not be the actual address, obviously, right? So that's why we have this logical to physical translation, right? So basically this is relocatable code, which means you can locate this code to anywhere. This is not necessary that you have to locate this code to, I mean, the code just like this variable have to be stored to the 5000. No, this variable could be stored anywhere. That's why this code that compiler is generating is called relocatable code, right? Why it is called relocatable code? Okay, can you confirm if the voice, I'm really sorry about the construction part that is going on. Okay. Are you hearing some extra noise? Can you confirm? I mean, now the construction just got stopped, but I think just before the few seconds. So this is called relocatable code because we are going to convert this logical address. That is something called logical address, right? This is called logical address, and that we are going to convert to physical address. And that's what logical memory mean. Logical memory just saying that you are basically something logical, some logical memory is there. I mean, there is some memory is there, and that is how we are going to run our program, right? Let me know if that part is clear about the logical memory. Now we will move to something called as virtual memory. So what is virtual memory then? If that is a logical memory, then what we call virtual memory? Can anyone quickly tell me what we call virtual memory? Okay. Uh, any guesses, like what is the difference between logical memory and virtual memory? What is virtual memory here? So virtual memory is just one additional concept on top of the logical memory, where we say that you do not need to even limit yourself, which means that there is a logical memory that I have, right? So this is the logical memory that I have, and the program, for the program we are saying that is the operating system, and you can expand yourself. I mean, you can use the complete physical memory. That's what we are saying in the logical memory, that the complete physical memory is used by you. Now virtual memory is saying that this memory that you're talking about is basically not just physical memory, it can be as large as your hard disk, because virtual memory allow your program to be stored. It is just one extra concept that allow your program to be stored on hard disk. Which means if I'm just saying logical memory, then it means that I'm not saying that you can do the demand paging, and that's also what also called demand paging. I mean, this virtual memory and can we actually like it can be implemented with the demand paging, with the demand segmentation, like these kind of things, demand paging, or maybe some other method, right? Or maybe demand segmentation. I mean, these are just a method to implement virtual memory, but the core idea is this, right? So let me just write the core idea and the methods both. So basically, the core idea, core idea that virtual memory says, or maybe core idea of virtual memory is like this. It says that what it says that you can store part of the process in the hard disk, part of the process in the hard disk. This is the core idea. And how to do it actually, which means the ways to implement it. Implement it. It means the virtual memory, right? It here means the virtual memory. The ways to implement it, basically, we are saying that you can use the demand paging. You can use maybe the demand segmentation, right? Or maybe whatever you think. I mean, like any other way, any other way. By which you can store process in hard disk. Anything, right? By which you can store the process in the hard disk. So that's what the idea of virtual memory. I hope that is clear to everyone, right? So the idea behind the virtual memory is that you can store your process in the hard disk. That's the idea about the virtual memory. Logical memory is saying that there is some logical memory that you have that is looking like this, right? Now if you run this program, then you can even have some part of this program in the hard disk. That's what virtual memory says. So if I'm saying just a logical memory, then it means that I'm not allowing you, or maybe I'm not implicitly saying you to store the program in the hard disk. If I'm saying virtual memory, then only I'm saying it. And how to implement this virtual memory? Maybe using demand paging, maybe using demand segmentation, or maybe some other way by which you can store your process in the hard disk. So that's the difference between virtual memory and the logical memory, right? I hope that is clear to everyone. Now, let's just see some of the gate problems that we want to solve today. So, what we want to do today, let me just tell you. So, today we will be seeing some of the very interesting problems in multi-level paging. Right? And now, today only, I will just maybe tell you some of the popular misconceptions. Or in other words, I can say most widely misunderstood concepts, right? Most widely misunderstood concepts about multi-level paging. That's what we want to do in this today's lecture using the gate PYQs. So this all should be done using gate PYQs. Okay, this is the today's agenda. Let me just start. Let's see this problem. What they are saying, in a virtual memory system, the address space specified the address lines of the CPU must be blank than physical memory and blank than secondary storage size. In a virtual memory system, it means that you can store your program in the hard disk. The address specified the address lines of the CPU. Okay, must be. So what should be the answer? Just think about it and let me know that what should be the answer. So CPU generates the logical address, right? Remember it, that CPU generates logical address. What does this mean? What does this mean to say the CPU generates logical address? Because in our compiler, we are saying that load, compiler has written that load R1 5000, which means CPU will just execute this particular instruction. CPU will not do anything else apart from executing this particular instruction, right? So now tell me what should be the answer. They are saying that the address the CPU generating, since CPU has to generate the logical address, and then they are saying the address line of the CPU, which means that whatever CPU generating must be, since see the relation is that the physical memory that you have, physical memory should be lesser than whatever your virtual memory you are allowing, right? You are saying that okay, you can extend to this point. Virtual memory means that you are just allowing your physical memory to extend, which means you can store some of the program in the in the hard disk. So let me just brief you. See, the logical memory just says that suppose you want to run this process, right? Logical memory says that suppose you want to run this process, which is basically logically is having from 0000, which is consuming from FFFF, right? Now logical memory says that if you want to run this process, then you can run it, and since it is relocatable code, that is fine. But the problem with this approach is that you have to run this in the main memory, right? This whole process has to be loaded in the main memory, and this logical memory says that you have to load whole of the process in the main memory, which means that if you want to run any just this instruction, right, this instruction which is nothing related to any other code or any other data, then also you are not allowing yourself or not allowing system to store some part of this process in the physical memory, in the hard disk. So basically you are asking all of this to be stored in the main memory only. That is the problem with the logical memory. But virtual memory allow you to store in the physical memory. So basic in the hard disk. So basically the virtual memory is just an extension of this physical memory. We are just having an illusion that physical memory is larger, right? So virtual memory is greater, and then your hard disk, which is called secondary storage. So they are saying that whatever CPU generating, which means the which means the virtual memory, CPU basically generate the logical address. I mean whatever address you write here, or it is better to say that CPU generate the virtual address if you are using the virtual memory, right? Because whatever address you are writing here, it is actually treated just like that. You are having memory from 000 to FFF. Now this is a virtual memory. Now it has become a virtual memory for you. Why? Because you are saying you can use a memory from, I mean the actual physical memory could be smaller, but you are saying you can use memory from 000 to FFF. So I hope you got it right. See, with the logical memory, you are just saying that you have to load. I mean, you do not know that you can even store in the physical in the hard disk. So this, with the logical memory, the physical memory and logical memory, if there is no virtual memory in the picture, right? If there is no virtual memory, then logical memory, whatever you are having, is exactly same as the physical memory if you do not have virtual memory in the system. which means this has to be loaded in the physical memory as it is. Right? That's what our assumption is. What virtual memory says that whatever you are having, if you are having the virtual memory, then this virtual memory becomes larger than the physical memory, which means you will say whatever you are having can be more than the physical memory, because you are allowing yourself to store in the hard disk. So this virtual memory can be more than the physical memory also. Okay. So CPU always generates the address virtual address, which means you are saying to your compiler that load, I mean you can use from 0000, maybe this is FFFF, you are saying from this to this you can use. So compiler will say load R1 and comma, maybe any address it can use, maybe let's suppose 5539, some address, right? Some address it can use. So basically you are saying like compiler is writing here the virtual address, compiler is writing here the virtual address, and then that's why the CPU will generate the virtual address. So CPU will be generating the virtual address in case of virtual memory system. So virtual address should be greater than, right, should be larger than, it should be larger, so either COD, then physical memory, and whatever the virtual address is should be smaller than the secondary memory. So I think C is the answer, right? Okay. Mahabit is asking something. Sir, it means the logical memory is less than or equal to the physical memory. Yes, yes, you can say this. I mean, if there is no virtual memory, then yes, you can say this. If there is no virtual memory, right? If there is a virtual memory, then we do not. Generally we do not use the term logical memory anymore, right? If there is a virtual memory system, then we just use a virtual memory. It is just a superset. I mean, you are just having now there is no logical memory. Virtual memory is basically combination of logical memory plus whatever you are allowing extra. Okay, in the virtual memory system, generally we do not use logical memory as a term. We just use the virtual memory. And if there is no virtual memory, there is only logical memory. Then in this case, yes, you are right. The logical memory cannot be greater than the physical memory. It should be lesser than equal to the physical memory, right? Okay. So yes, C is the correct answer, right? Cool. Now let's go to this question. What they're asking is that which of the following is your advantage of virtual memory? Now they're asking about the advantage of virtual memory. Can you tell me what is the advantage of virtual memory? Faster access to the memory on an average. Virtual memory is saying what? It is saying that you can have larger than the physical memory, right? One thing it is saying that you can have larger than the physical memory. Let's suppose this is virtual memory that can be larger than your physical memory. Second thing is it is saying since it is larger, so obviously you cannot store all of them in the physical memory. That is why it is allowing yourself to store in the hard disk also. So is this the faster access? I don't think, right? I mean, if you are allowing it to store on the hard disk, and if by chance if you need to bring some, let's suppose the CPU is generating 5000 address and you have not stored, let's suppose this is the 5000 address, but let's suppose you are using paging and this page is in the hard disk. Let's suppose it is in the hard disk. Okay. Now in this case, I don't think it will be the faster access, right? You might need to bring, in case of page fault, that is called page fault, that we will talk about tomorrow, but yeah, in that case you might need to bring some pages in the main memory, or maybe in general if you're using paging, then it is like multiple access that you need to do for the virtual memory. I don't think that it is a faster access in any case, right? Process can be given the protected address spaces. Okay. So with the virtual memory system, the processes can be given the protected address spaces. Yes, it seems true, right? Why? Because virtual memory is saying that this memory, this from here to here, this is your area, and then you will be storing that in the physical memory, right? And then obviously, like for every process, I'm saying that this is a different memory you are using. For every process, there is a different virtual memory that is having the same size, right? So for every process, I'm providing different virtual memory. I'm not saying that this is the same virtual memory that you need to share. So basically what will happen, that there is just one physical memory that you have. This is just one physical memory, and logically, right, we are saying that there is some virtual memory for different process. This is virtual memory for this process, this is virtual memory for this process. Now what will happen, that we are storing maybe some pages of this process in the physical memory, maybe some pages of this process in the physical memory, and some pages of these processes are might be in the hard disk also, right? Have to be in the hard disk even. I mean, if these pages we do not have any space, then let's just bring them to the hard disk. So what they're saying, you are providing a separate access. Yes, this is protected area, right? I mean, this process will be just dealing with its own virtual memory. This process will be dealing with its own virtual memory. Now the virtual address could be same. That's very interesting. See here, the virtual address could be same. Let's suppose there is a virtual address. Just listen here very carefully. There is a virtual address 5000, and this virtual address the variable age is stored, and that is having value 5. Now at this virtual address is also 5000. At this virtual address, let's suppose the variable b is stored. Do it have to have the same value? Tell me. Or it can have any value, right? Let's suppose it is having 37. Why not? So the virtual addresses could be same. Still, the value at that address could most probably it will be different only, right? So the virtual address will be same, but the value stored at those virtual address will be different. But interestingly, those physical address will be different. Obviously, this 5000 will translate to, let's suppose this is 2000, and this 5000 will be translating to, let's suppose this is 10,000, right? I mean, this 5000 physically it means the 10,000. This 5000 physically it means it is 2000. Since the physically these are the two different locations, that is why it can have 5 in it, it can have 37 in it. It is the value of b, it is the value of a. So physically a and b are at different locations, but logically these two could be at the same location. Do you remember we did one example of fork in first lecture, I think, right? In that I told you that how it is happening. I mean, the logical address, it copies the whole virtual address of the logical address, and that's why the logical address of the virtual address could be same. Still, the physical addresses are different, right? Okay. I mean, still the values are different. I hope you understood. Now, what they're saying that yes, we are giving the protected area. Linker can assign addresses independent of where the program will be loaded in the physical memory. See, this is yeah, that I agree. I mean, linker can assign, basically linker just bind the addresses, but it is not about the I mean, advantage of the virtual memory, right? Or do you think this is advantage of virtual memory? So what this option is saying, see, linker comes before the virtual memory. I mean, even before running, you do not even know whether you are using virtual memory or not, right? I mean, to the compiler, we do not tell that we are going to store some of the pages in the hard disk or not. It is up to us that how we are going to manage the memory. To the compiler, we just say that this is a logical memory that goes from here to here. So to the compiler, we never reveal the thing that we are going to use virtual memory or not. Like, I mean, from the compiler perspective, it's not even needed. From the compiler perspective, what is needed is that your address is starting from this one and ending from this one. That's all, right? I mean, you can use any address from this one to this one. That's the compiler needs. So compiler do not need to know whether it is virtual memory or it's just a logical memory. So after the compiler, there will be a linker, and linker also just binds the addresses. It doesn't need to know whether it is a virtual memory or not. So linker is just I mean, far before than the virtual memory comes in the picture, which means virtual memory we require at the runtime, but linker is even before at the runtime. So that's why C is not the correct answer. I mean, that is the correct line, but it is not advantage of virtual memory. Okay. Program larger than the physical memory size can be run. Yeah, that is also true. This is also true. So these two are true. Let me know if that is understood. Right? Okay. Yeah, B and D are answer. So yeah, for C option, let's just see what it is written. Position independent can be produced even without the virtual memory support. Yeah, that's very nice line. I mean, if you want to produce a relocatable code, you do not need to use virtual memory. Just a logical memory can do, right? Okay, it is true. As okay, B and D are true. So I hope you understood this. Now tell me just one doubt. I mean, I want to ask you one thing. Suppose you are using only virtual memory. Suppose we are using just virtual memory, right? There is no logical. Oh, sorry, we are using just logical memory. There is no virtual memory. Which means no virtual memory we are using. And what does this mean? It means that whatever is your physical memory, right? Whatever is your physical memory, in that memory only I need to store everything. I need to store my whole process in that memory only. So let's suppose my logical memory is just smaller. See, logical memory just says that your address will start from, let's suppose, 00 to FF, right? This is just a logical memory size. It doesn't say that what is the size of it. Could be lesser than the physical memory, right? It is very much possible that the logical memory could be lesser than the physical memory. Let's suppose that this is the logical memory you have, right? And let's suppose the physical memory is just 3 to 4 times of this logical memory, which means if this is, let's suppose, 10 kb, okay, I mean maybe 10 MB, and let's suppose it is just 10 times, which is 100 MB. Okay, now can you tell me that, I mean, I'm just asking you roughly, okay, let's not worry about too much about the operating system space. Let's forget about the operating system space. Okay, now can you tell me that how many processes you can run in this system at a time? Okay, let's forget about the operating system space. So tell me how many processes we can run at a time. This is your logical memory, this is your physical memory. And what do you think? See, logical memory, the problem with the logical memory is that it says that all of this process has to get fit in the physical memory. There is no chance you can store in the hard disk. So since you cannot store more than 10 processes, that's why only 10 processes are allowed, right? I hope you understood this. See, the limitation with the logical memory is that you have to store all of this in the physical memory. Since you have to store all of this in the physical memory, so I don't think more than 10 processes, right? Okay. Okay. Mahabhat is saying that if MCQ, then only D. D is this program larger than the. No, it's not like that. I mean, the MCQ and MSQ cannot change the answer. The answer is fixed, right? I mean, if it is MCQ or MSQ, it doesn't mean that it can change the answer. So it is whether it is MCQ, then it is marks for all. If it is MCQ, then it is marks for all, right? It is not that if you convert the MCQ to MSQ, then answer the options will get limited. Something is correct, then it means correct. It is correct, right? Sometimes, yeah, it is possible that it might be more convenient as one point, but I think if something is correct, I mean, if they say, if they either they ask only one of the option that what is the most correct, then you have to make a trade off that okay, you, I mean, over this you will be choosing this, but these two options are independent, right? I mean, in this case both are correct. This is not like MSQ or MCQ here. Okay, so Mohammed is saying only one can run because we assume one CPU. I mean, what I meant to say that concurrency, I meant to say the concurrency, right? Which means that you can load 10 processes in the main memory and then you can schedule one after another, right? I mean, at the ready queue and the running queue together it could be 10. And then since you have having only one CPU, then obviously at a time only one you can run, but you can provide the concurrency, like you can switch between the processes. But at a time you can load 10 processes in the main memory, right? In the earlier example that I was talking about, in this example. Okay. And what about the virtual memory? Suppose if I have the virtual memory, then maybe many processes I can do, right? Okay. Let's just do this question. Which of the following is false? Virtual memory implements the translation of programs address space into the physical memory address space. Just take your own time and let me know if which are true and which are false. They are asking about the false, right? Virtual memory implements the translation of a program's address space. Program's address space means virtual address space. Okay, into physical address space. Yes, it has to implement. If you're using the virtual memory, then yes, it has to implement. Why? Because your physical memory is whatever it is, OS it is here. Then in this physical memory, you are not implementing the. I mean, you are not loading this process as it is, right? Maybe some part you are loading here, some part you are loading here, like that, right? So that is why it has to implement. So this is actually true. Virtual memory allows each program to exceed the size of primary memory. Yes. Virtual memory increase the degree of multi-programming. Yes. Which means you can provide the concurrency. Multi-programming means you can load multiple programs in the running in the main memory. Virtual memory reduce the context switching overhead. No, there is no relation, right? I mean, virtual memory has nothing to do with the context switching overhead. So that's why it is false. Is this okay to everyone? Yes, Mahavit, that is correct. So now let's move to the next question. D should be the answer. The main advantage of virtual memory is increased address space for the program and the independence of the address space, which allow more degree of multi-program as well as option for the process security. Okay. Virtual memory requires switching of the page table, that is done very fast by the switching of pointers for the new process and thus theoretically slower than without the virtual memory. Any virtual memory directly decrease the doesn't directly decrease the context. Like there is no relation between, I mean, context switching overhead is different and virtual memory is different, right? Even with the virtual memory, we might be even increasing the context switching overhead. Maybe we might be having different page tables, so I need to also maintain the page table thing. Okay, anyway. Now let's just understand that this multi-level paging and how does it look like and what do we mean to have the multi-level pages, right? So since this is just a revision class, so that is why I will not go to very much theoretical details. I will just have some brief introduction, then we will be just solving the questions. So suppose that this is your logical address space, right? Logical, or maybe let me write virtual address space. Which means that your virtual address space is having, let's suppose 8 and 8 16 and 6 22 and 10 32, right? So it is 32 bits, it is having 32 bits. Now I'm saying that I'm dividing my logical address space into these bits, I mean 10 8 8 6. Now let me quickly tell you that what does it mean to say that we are dividing into that. What does this 10 means? It means that at this level, okay, so there are different levels at this level there, and at every level I have some chunks. I mean, okay, let me tell you in very detailed way, because that is one of the most as I said, like most popularly misunderstood concept. So see, this is, let's suppose, top level, that I'm calling it first level. Okay, now tell me how many page tables, or let me just call it chunk, how many chunks are there in this first level? How many chunks are there? See, each chunk will be having, this 6 will tell you that how many entries are there in each chunk. So number of entries in each chunk is one thing. Another thing is that at every level, number of chunks, how many chunks you have, right? So there are two things that I want to ask. Another thing is that number of chunks at this level. Can you tell me what is the number of chunks at this level? Okay, this is the first one. This is maybe the second one. So number of chunks. Since it is a topmost level, that is why I will say the number of chunks in the topmost level is just one, right? So it will be just one. Let me write one. I hope you understood this. Number of chunks in the top level is always one. Now, what about number of entries in each chunk? Since it is just one chunk, that is okay. So how many entries you have? 2 power 6 entries. I'm talking about the entries. Okay. So I hope that part is clear to everyone. Now, what about the number of chunks at this level? Or maybe can you tell me first number of entries in each chunk? This 8 represents the number of entries in each chunk is 2 power 8 entries. This 8 represents the number of entries is 2 power 8 entries. This 10 represents the number of entries is 2 power 10 entries. But at the last level, each entry has just 1 byte. So you can also say 2 power 10 bytes, right? I mean, see, these are the entries, but at the last level, it is just 1 byte. So I mean, if you want you can say entries, but since at the last level you just have each entry just 1 byte, because memory is byte addressable. I mean, in most of the cases the question memory will be the byte addressable. So in that case you will say that each entry will be just 1 byte, so that is why it is just 2 power 10 bytes. In the last it is very easy to convert entries to the bytes, but here you need to multiply with the page table entry size. Anyway, I will talk about it later. So is this clear to everyone? There's what does the 6, 8 and 8 and 10 represents, right? So I'm just doing quickly with the revision. Okay, now tell me how many chunks are there at this level? It was 1. At this level, how many chunks are there? See, this, if you want to find out the number of chunks at this level, you have to go till to the previous levels. Sum up all the bits here. This is 6, so you will say 2 power 6 chunks are there. 2 power 6 chunks you have here. This 8 represents the 2 power 8 entries are here. But if you want to find out the number of chunks at this level, then it is 8 plus 6, which is 2 power 14 chunks you have here. This 10 represents that, okay, 2 power 10 entries you have at the last level, but if you want to find out the number of chunks, then you will be saying here the chunks is just the pages, but anyway, this is 8 plus 8, 16, and then 6, 2 power 22 chunks. Okay. So this is what address division mean. I mean, each entry represent that how many each of this number represent that how many entries are there in each chunk, and then if you want to find out the number of chunks, then this will represent the number of chunks. Let me tell you in more detail, then it will be more clear. Okay, so because it is very important concept, that's why let's just spend a few more minutes in that. So what I want to explain is this. See? Okay, just see here that what I want to say. Suppose initially let me just assume that you don't have this address split. Initially whole thing is just 1, which means this is 10 bits. Now can you tell me what is the remaining number of bits that you have here? If this is 10 bits, then you will be having 22 bits here, right? Okay, let's just deal with this first, and then we will deal with the other part later. This is 10, this is 22. Can you tell me what does this 10 and 22 means? It means that each page is having 2 power 10 size. I mean, here let me just call it chunk. Okay, so chunk size is 2 power 10, and how many such chunks or how many such pages are there? These are 2 power 20 pages, right? So basically this 22 represents that you have, since this is just one flat level page table, you have 2 power 22 entries, right? So this 22 represents that you have 2 power 22 entries, since this is just flat level page table. So this is 2 power 22 entries, and each entry is pointing to one page which is having 2 power 10 entries, right? I mean, this 22 represent 2 power 22 entries, this 10 represent 2 power 10 entries, like that, right? So each is pointing to something which is having 2 power 10 entries. Now what is size of this chunk? 2 power 22 entries into page table entry, whatever the size of one entry. What is size of this chunk? 2 power 10 entries into, just for the last chunk, it is bit special. I say that each entry actually contains just 1 byte, so just 1 byte. Okay, always it is just 1 byte, which means it is 2 power 10 bytes. Is this clear to everyone? This is very important concepts that we are going to discuss now. So this is 2 power 10 bytes, and this is 2 power 20 into some page table entry. Basically you can convert the entries to the bytes. I'm just trying to convert the entries to bytes. If you want, you can convert, or otherwise we can talk about it little later, right? So this is 2 power 10 entries, this is 2 power 22 entries, which means there is a page table here that is having 2 power 22 entries. There is a chunk here which is having 2 power 22 entries. There is a chunk here which is having 2 power 10 entries. Now how many such chunks are there? Okay, number of chunks. Let's talk about number of chunks at each level. There is just one chunk at this level, it is outermost. This chunk will be having 2 power 22. This level will be having 2 power 22 chunks, which means each chunk is having 2 power 10 entries, and there are such 2 power 22 chunks, or if you want you can call it pages, right? I hope that is clear. Now let's just do one thing. Let me divide this page table. Okay, let me divide this page table maybe in such a way that maybe let me just group them maybe in such a way. Okay, this is 8, right? Okay, So maybe in such a way that each group, let me just divide into the groups, each group is having just 2 power 8 entries. See, what I am saying here is that you have 2 power 22 entries here. Now let me divide this in such a way that each is having 2 power 8 entries. This is having 2 power 8 entries. This is having 2 power 8 entries. This is having 2 power 8 entries. Something like this. Right? Is this okay to everyone? If I just divide this page table into in such a way that each one is having 2 power 8 entries. Okay? Okay. I hope that is clear, right? Now one thing, tell me that at this level how many entries I had total? 2 power 22 entries. I am just dividing it. Will this division will reduce the number of entries here, or it will remain same? Which means I had I had 2 power 22 entries here, right? I have 2 power 22 entries here. What I am asking, if I group each the entries in 2 power 8, 2 power 8, 2 power 8, 2 power 8, such that like each group is having 2 power 8 entries. Now in this case, the number of entries that I am having currently here, will it decrease or it will be same? Obviously it will be same, right? I mean, just by grouping I cannot decrease the entries. Nobody can decrease these entries. This is 2 power 22 entries, means it is 2 power 22 entries. Nobody can decrease these entries. What if God comes? Can God decrease these entries? No, right? I mean, these entries are fixed, which is 2 power 22 entries. Okay. Now, this is 2 power 22 entries. I am just dividing these 2 power 22 entries in 2 power 8, 2 power 8, 2 power 8 entries. So, which means that now in the I'm basically creating one more level of page table, right? And in one more in the next level page table, how many groups are there? Number of chunks. Can you tell me number of chunks? If each chunk is having 2 power 22 entries, 2 power 8 entries, total 2 power 22 entries, 2 power 8, it will be 2 power 22 minus 8, which is 2 power 14. So there will be 2 power 14 chunks, right? So number of chunks now here, instead of 1, it will be 2 power 14. And since there are 2 power 14 chunks, that is why I will be having 2 power 14 entries here, because each entry will just point to one chunk. Right? There are 2 power 14 entries. And number of chunks is now it is just one chunk. Okay, I mean earlier one chunk was here, but now this is just one chunk. Each chunk is having 2 power 14 entries. I mean there is just one chunk. And here there are how many chunks now? See, earlier it was just one chunk, but I have divided that one chunk into some groups. Okay, how many groups I will be having? If each group is having 2 power 8 entries, then there will be 2 power 14 groups. Is this clear to everyone? Okay, so I hope that is clear. Let me know if there is any doubt. So there will be 2 power 14 groups. Why? Or maybe 2 power 14 chunks, because each chunk is having 2 power 8 entries. So I will say that this 22 has been divided into two parts, something like this. Maybe since this is having 2 power 8 entries, so number of entries I will be writing here. This is having 2 power 14 entries, so 14. So I have divided this 22 into two parts, 8 and 14. This 8 will represent number of entries in this chunk. How many chunks are there? This 14 will tell you. The 2 power 14 chunks, right? And this 14 will represent how many entries are there? 2 power 14 entries. How many chunks are there? At the outermost it is 1. How many chunks at this point? 2 power 14. How many entries in just one chunk? 2 power 8. How many chunks at this point? Can you tell me how many chunks at this point? Okay, how many entries at this point? 2 power 10 entries in just one chunk. How many chunks? There will be given by this 2 power 22 chunks. See, earlier also it is 2 power 22 chunks, right? I mean each entry is pointing to one chunk. Earlier also it is 2 power 22 chunks, and now also it is 2 power 22 chunks, right? I mean at this level nothing has changed. At this level also nothing has changed. At this level the total entries earlier was 2 power 22 entries. Now I am saying there are 2 power 8 entries in one chunk, and since each chunk and there are 2 power 14 chunks, so if you just multiply 2 power 14 number of chunks into in each chunk number of entries 2 power 8, so there are again 2 power 22 entries. See, these are total 2 power 22 entries. I just divided it. So nothing has changed at this level also. It is just a division that we are doing, which means we are just creating one more level of hierarchy. No, how number of entries cannot reduce. I mean, the total number of entries are 2 power 22, which means 2 power 22 here, right? I mean, you can say in one chunk, obviously in one chunk it will be lesser, but total number of entries 2 power 22 means 2 power 22. Nobody can reduce it, right? Earlier it was 2 power 22 entries. Now I'm just doing what? I'm just doing groupings. If I'm just doing grouping, it doesn't mean that I can reduce something. I'm just having it one more level of page table. It is just groups now, right? It is just groups. Let me know if that is clear to everyone. Now let's just do one thing. Okay, so let's just take it and let's just divide this 14 also into further parts. So see, let me just quickly summarize you what has happened here. So this was earlier like this. This 10 means that there are 2 power 10 entries in one chunk. How many such chunks? 2 power 22 chunks. It will be given by this 2 power 22 chunks. Here, how many entries? 2 power 22. How many chunks? Since it is outermost one chunk, right? Now I divided this 2 power 22 entries into two parts. Each one is having 2 power 8 entries. How many such chunks? 2 power 14 chunks. Total 2 power 14 into 2 power 8, which is 2 power 14 plus 8, which means 2 power 22 entries. Again 2 power 22 entries here, right? Okay. Now let's just see what this picture currently mean. This picture means that there are 2 power 8 entries, right? At this level there are 2 power 8 entries in one chunk. 2 power 8 entries. At this level there are 2 power 14 entries in one chunk. 2 power 14 entries. At this level I am saying there are 2 power 10 entries in one chunk. So this is just entries, right? These entries. Now if someone asks me how many such chunks are there, this is just one, right? How many such chunks? So each is pointing to one chunk. Each is pointing to one chunk. So that's why how many such chunks at this level? Since each entry is pointing to one chunk, that is why there are 2 power 14 such chunks, right? Each is having 2 power 8 entries. So how many total entries are I am having? 2 power 8 into 2 power 14. This is total entries, which is 2 power 22. Anyway, so now this is pointing to each chunk of size 2 power 10. How many such chunks are there? Since there are total 2 power 22 entries, that is why there are total of 2 power 22 chunks, right? There are total of here you have number of chunks. Let me write number of chunks. The number of chunks will be given by this number, which is 2 power 14, because that is representing number of entries. Now number of chunks here will be, there are 2 power 14 chunks, each is having 2 power 8 entries, so 2 power 22 total entries. So that's why number of chunks here will be 2 power 22, right? Each is having 2 power 10 entries, 2 power 10 entries. So there are 2 power 22 chunks, or maybe at the last you can say pages. Okay. So this is the current picture now. Now what we will do, we will just divide this 2 power 14 into multiple parts. We will say, okay, let me just divide this also into the multiple parts, right? So I mean, it depends how we are dividing. You can divide in any number of parts. Let's suppose again I am saying that each chunk is having 2 power 8 entries. Each chunk is having 2 power 8 entries. Okay. So let's suppose I am dividing in such a way that each chunk is having 2 power 8 entries. So since each chunk is having 2 power 8 entries, that is why this is 8, and that is why you can say that each chunk is having 2 power 8 entries here. So these are 2 power 8 entries. So how many such chunks will be there? Total 2 power 14 entries. Each chunk is having 2 power 8 entries. So that's why 2 power 6 chunks will be there. So this is chunk number 1, chunk number 2, like that. There will be total 2 power 6 number chunks, 2 power 6 chunks. If I start from 0, anyway, like that, these many chunks will be there. Each will be having 2 power 6 and 2 power 8 entries. So it will be 6. So which means at the last level you have 2 power 6 entries, and there is just one chunk, right? So that's what this address split mean. Now let's solve few of the question. I hope you understood this address split. That is very, very, very important, right? Okay. See here, what does this 6 means? that you are having 2 power 6 entries, and whatever the number here, let's suppose this is 0 1 0 1 0 0 or whatever number, right? In this 8 bits there will be some 0 1 0 0 1 0 0, whatever the number here, that represents the offset, which means since there are 2 power 6 entries, it will tell you that which entry you are talking about. This number will tell you that which entry you are talking about, right? This number will tell you that which entry you are talking about, which means since there are 2 power 8 entries, that's why it will just point to one of the entry. It will just point to one of the entry. It will just point to one of the entry, like that, right? And this is the base register. So this is, yeah, that's also very, very important to understand that this is having the address of a chunk, right? This is having an address of chunk. So this is having address of a chunk, and the chunk size is 2 power 8, right? I don't know if you are able to understand, but I'm expecting if you attended the classes, then definitely you must be able to understand, right? Just like, I mean, I'm sure the Akash, Mahavit, these people have attended the classes. So Akash, Mahavit, can you confirm if you can understand everything? Okay, Mahavit is asking, sir, what is the answer for number of entries in the third level page table if outermost page table is level 1? Number of entries in the third level, 1, 2, 3. Number of entries here 2 power 22. Number of entries is a third level page table. I mean, they will specify what does this page table mean. Okay, I mean, actually this page table is bit wider term to say. They will specify that they are asking about the just one page or the total entries. Okay, so just one page will be having 256 entries, but the total will be 2 power 6 2 power 6 plus 8, which means 2 power 14 entries, right, total, and one chunk will be having just 2 power 8 entries. So I mean, number of chunks will be 2 power 6 plus 8. These are the number of chunks at this level. Each is having 2 power 8 entries. So there will be 2 power 14 into 2 power 8, which is total 2 power 22 entries. They will specify that what do they mean by the number of entries. Okay. Okay. Cool. Now maybe we can do some of the questions, right? Okay. Let's just do this question. Consider a machine with 64 MB physical memory and 32-bit virtual memory address space. If page size is 4 KB, what is the approximate size of page table? So virtual memory is given to be 32-bit and physical memory is given to be 64 MB. 64 MB means 2 power 6 into 2 power 20, which is 2 power 26 bytes, right? And like most probably it is byte addressable, so that's why these are the 26 bits you have for the physical memory. If page size is 4 KB, which means 2 power 12 bytes, then it means for the physical memory 12 bytes for the page size. 12 means this is also 12. So remaining is 20. Here the remaining is 40, right? What is the approximate size of page table? Okay. Now they are asking if this is a flat level page table, what is the approximate size of this? So how many entries are there? 2 power 22 entries in each chunk, right? 2 power 22 entries, but there is just one chunk, so that is fine, right? Now they're asking about the about this page table size. What it is storing? That's very important. What it is storing? It is pointing to something that is having 2 power 12 entries, right? Or 2 power 12. I mean, in this case it will just bytes, but yeah, in general it is 2 power 12 entries. But since it is the last level, it is just 2 power 12 bytes. So since it is storing 2 power 12 bytes, which means that it is pointing to something which is basically storing 2 power 12 bytes. So how many such chunks will be there or such pages will be there? 2 power 14. So that's why it needs 14 bit to address this, right? I hope you are getting. So this will be 14 bits, and then this is 2 power 20 number of entries. 2 power 20 into 14 is approximately 16, I'm writing, so which means 2 power 4, right? So it is 2 power 4 into 2 power 20, which is 16 MB. So A is the correct answer. Okay, C. Sorry, this is the bits. So 16 megabits, or maybe let me directly convert to the bytes. So you can divide by 2 power 3. So this is 2 MB, right? Okay, so I hope that is fine to everyone. Now, one very important point here is that, see, what is happening here, there was a logical memory, this is some bytes, maybe bar A, this is 20. Now here you have 2 power 20 entries, right, 2 power 20 entries. Now each is pointing to something which is basically having 2 power 12 entries. Can you convert that to bytes? Since it is last level, so 2 power 12 bytes only. Now that's very important to understand that this is having 2 power 12 bytes. So that is why the number of bits here, now the, see, ultimately everything is in the physical memory, right? Now if you have to store that in the physical memory, then how many such chunks will be available? The physical memory is of size 26 bits, so you will say 26 bits is the physical memory. So that is why if you want to store these kind of chunks, so you will say that there are, if it is 2 power 26 bytes, there are how many chunks will be available? 2 power 14 chunks, right? So basically there are these such chunks are 2 power 14. Since there are 2 power 14 chunks are available here, it need to address one of the chunks, so that's why 14 bits I need to write here, right? Okay. Now let's just mold this question little bit, which has been actually asked in GATE. This, let me just tell you, there is one very important GATE question. Yeah, GATE 2008. So that question also has been asking GATE 2008, and that's very nice question. See, suppose they ask it little bit, they just modified it a little bit, and then they say your logical address space or maybe virtual address space is looking like this. They say maybe it is, let's suppose 12, maybe it is, let's suppose 8, maybe it is 6, maybe it is 4, something like this, which means it will be 10 and then 20, this is 30 bits your logical addresses. Okay, suppose something like this. Then tell me, what is the scenario? I mean, what does this mean to say? It means that there are 2 power 4 entries here. In each chunk will be having 2 power 4 entries. 2 power 4 entries. Each chunk will be having 2 power 4 entries, right? Okay. Here, how many entries each chunk will be having? Just listen very carefully. Here, each chunk will be having 2 power 6 entries, right? Okay. Now tell me how much the number of bits it need to address this kind of structure. I mean, this kind of chunk. This is my question. You got my question? My question is that number of bits it need here, because it has to point to one of this chunk, right? It has to point to one of the other chunk. It has to point to one of the other chunk, like that, right? It has to point to one of the other chunk, and there are 16. It has to point to one of the other chunk. So how many bits you need here to point it? How many bits you need here to point another chunk? That is my question. If, let me also give you, if your physical address space is let's suppose it is some bits, okay, it is, let's suppose 20 bits. Have you understood my question? How many bits you need here? See, and also, sorry, one more thing, page table entry is, let's suppose 2 bytes. One more thing I need to give you. Okay, so this is physical address space, this is page table entry, and my question is simple, that how many, since it is pointing to one of this chunk, how many number of bits you need to point to one of this chunk? See, there are 2 power 6 entries, right? So it is pointing to something which is having 2 power 6 entries, but let me convert that to a bytes. So which means 2 power 6 into 2, because the page table entry size is 2, which means 2 power 7 bytes. So it is pointing to something which is having 2 power 7 bytes. So that is why you will say that there are, since the physical address space is 20 bits, that is why you will say there are 2 power 13 such chunks, I mean could exist. So basically you have to divide the physical address space, which is 20 bits, in something like this. This is 7, because 7 you will be needing for this, and then there is 13. So which means there will be 2 power 13 such chunks, because 2 power 7 bytes is if that is the size of this chunk, then there could be at most 2 power 13 such chunks that you can store in the physical memory, right? So basically you need 13 bits here. Yes, Mahavit, that is correct. So this is very, very important to understand that you need 13 bits here, right? Once you understand this, then it will be, I mean, these multi-level kind of questions will be quite easy for you. Okay. Now tell me how many bits you need here. How many bits you need here? Since it is pointing to something which is having 2 power 8 entries, which means 2 power 9 bytes, which means your physical address will be divided like this. This will be 9, this will be 11. So you need 11 bits here. You need 11 bits here. So it should be clear to everyone. You need 13 bits here. You need 11 bits here. And how many bits you need here? Since it will be pointing to something which is having 2 power 12 entries. And here, if you want to convert the entries to the bytes, it is just 2 power 12 bytes. So your physical address space will be 12 and then 12 and then 8. So you need 8 bits here. You need 8 bits here, right? You need 8 bits here to point to the next level. You need 11 bits here. You need 13 bits here. That question has been asked in GATE 2008, and that should be understood to everyone. The number of bits, because if this is clear to you, then you have understood multi-level paging in and out. Everything about the multi-level paging you must have got it if you can understand this particular diagram, right? So this particular diagram is very, very, very important. Let me know if there is any confusion in this. Okay. So that is clear. Let's move further. Then you can solve maybe most of the questions. Now let me maybe directly go to the PYQ. So what they are saying, a computer uses 32-bit virtual address and 32-bit physical address. So virtual address space is 32-bit and physical address space is also 32-bit. The physical memory is byte addressable. Okay. The page size is 4 kilobytes. So which means the physical address space, if you want to store this page, then since it is 32, this is 4 kilobytes means 2 power 2 into 2 power 10, which means 2 power 2 into 2 power 10, which is 2 power 12 bytes. 4 kilobytes means this. So it is 12. This is 20, right? It is decided to use two-level page table to translate from virtual address to physical address. So basically, they are saying that virtual address space, physical address space, both are 32 bits. This is also 32 bits. Now, physical address space is having some page of size 12, and then if you divide the physical address space for the pages, then it will look like this. Similarly, for the virtual address space, look like this, right? Okay. Now you want to use two level of paging. Now that's very, very important, this line. They are saying equal number of bits should be used for the indexing first and second level page table. See, this must be given. This address split must be given, which means that, see, virtual address space currently is looking like this, which means this is 12. Now remaining is 20. How to split this 20? There are millions possibility, which means you can split this 20 like this, which means 3 and then 17, right? Maybe you can split like this, maybe this is 3, maybe this is 17. You can split in any number of the ways. There are many possibilities. They have to give you that how you should be, I mean, splitting this. They are saying the equal number of bits are used, which means they are saying 10 and 10. Okay, they have to give the address split. You cannot calculate the address split. That is the most widely misunderstood concept. People think that we need to calculate the address split based on the something called fitting that page page in the main memory or something like that, right? So there is one misunderstood concept. Let's not talk about it. I mean, they say that this address split is actually forced, which means you have to fit this page into this page table, this page table into one of the pages or something like this. So there is some misunderstood concept, and let's not go with this. So they have to give you the address split, right? They're saying 10 and 10 are being used, and size of the page table entry is 4 bytes, right? This is your virtual address space. Give a diagram showing how a virtual address space will translate to physical address. So how you will translate? This 10 means what? See, this 10, 10, 12, right? This is 10, this is 10, this is 12. This 10 means what? There are 2 power 10 entries. And how many chunks are there? Only just one chunk, 2 power 10 entries. And this 10, whatever this is, 0, 1, 0, 0, 4, 5, 6, 7, 8, 9, 10. Let's suppose these are the 10 bits you have. This will tell you that which entry I am talking about, basically, right? So this will tell you, okay, let's suppose I'm talking about this. Then there are how many entries here? Again, there are 2 power 10 entries. And how many chunks are there? There are many chunks. I mean 2 power 10 chunks actually. So there are 2 power 10 entries. It will be pointing to just one of them. So see, this will be pointing to just one of them. There are many chunks. This will be pointing to just one of them, and this 10 will tell you that where to go inside this. Now there are many such chunks, each is having 2 power 12 entries, right? Each is having 2 power 12 entries. So this is having basically 2 power 10 entries. This is having 2 power 12 entries. Now each will tell you, so these are 2 power 12 entries, and this will point to one of them, right? Okay, and each will tell you just one byte. I mean, this is having just storing one byte. So this 12 will tell you that where to go inside this. Okay, whatever this number, this will just index it. So that's how you will be converting your physical address. Basically, how you will be converting to the physical address, you will get to know that, okay, if you want to, I mean, whatever address you have generated, so this will be some address which is, let's suppose, virtual address. Whatever address you have generated, you will check that, okay, that you go here, you go here, you will find the address of the, basically the physical address. So this is actually containing the physical address, right? Physical address of this chunk, and this is the physical address of this page, right? So finally here you will be finding the physical address of this page, right? So what you will do, whatever you got from here, right? Maybe you can do one thing. So whatever you got from here, okay, this is the physical address of the page that you have. So let me just tell you the total translation that is happening. So you will say that finally you got the physical address of the page you are looking for. It's still not the exact byte, right? The physical address of the page you are looking for. Physical address of the page we are looking for, right? Or the frame we are looking for. So you will put this physical address here as it is, and you will put where to go offset here. So this is the physical address of page. This is page offset. And this is the translation. This is the physical address you were looking for, right? Or maybe another way of saying is that this is the physical address of the page. Inside this page you will go here. So basically this address, right? Wherever you will go here, this address, this is the actual byte you have stored. So this address that after this 12, so I mean you will go here, and then whatever this address is, you will add 2 power 12 here. I mean sorry, whatever number this number is, let's suppose this number is 5000. So let's suppose this is x. So you will, I mean, this is storing x, this is storing x, which means this address is x. You will say x plus 5000 is your final physical address, right? And like it also works in binary. It also works like that. You can write your page offset directly here, and then I mean I'm not going to show you the calculation, but yes, it is equivalent to this. It is equivalent to this x plus 5000. How we can easily come to this conclusion if we try it. Okay, I mean binary things are very convenient. Let me know if that is clear or there is any doubt here. Is this fine to everyone? Okay. So I hope you are getting. If there is any doubt, let me know. If you are getting, then please let me know that this everything is clear, so that I get to know. I'm only hearing from 2-3 people, so it is better if you just convey the point. Okay. Yeah. So I think the diagram is clear to everyone. So this diagram is quite important. I hope that is clear, right? Now, what is the number of page table entries that can be contained in each page? Number of page table entries. I think you can find it. Number of entries here, right? In each page is 2 power 10, 2 power 10 like that, right? So yes. How many bits are available for storing the protection and other information in each page table entry? Yeah, that is a nice question. That if the page table entries are of 4 bytes, then tell me how much you will be needing to point it. So it will be basically having, see, it will be having address of this. This is 2 power 10 entries, and if you convert that to a bytes, page table entry is 4 bytes, which means 2 power 12 bytes, right? So your physical address space is of 32 bits, so it will be having 22 bits. No, sorry, 20 bits. 20 bits it need to address it. Similarly, this is 2 power 12 entries, which is 2 power 12 bytes again. So it will be again coincidentally it will be just having 20 bits, right? So how many bits are available? Since it is 4 bytes, which means 32 bits you have for the page table entry, 32 bits, and 20 bits you are using to for the address. So which means 12 bits your 12 bits are available, right? 12 bits you have for the other production bits and all. Okay. Yeah, we will be taking more examples. Don't worry. Okay. So see, 12 bits you are available. This 12 is written here. 12 bits are available for the other information, because you will be needing 20 bits for the for this physical translation. So let me just summarize everything probably. Okay. Let me just summarize. See, the address split could be anything. Again, the address split could be anything. Let me take one of the address split. Let me just tell you what does this address split mean. Let's just say, let's just take any address split. Maybe I have used one of them. Maybe let me just copy this. So let's just say that your address split is this, which means you can divide your logical addresses or your virtual address space in any way, and that has to be given to you. You cannot calculate it. You cannot be. I mean, there has to be some hint to calculate it. You cannot guess it basically. Okay. Okay. Moving further, you should be knowing what does this each number mean. What does this 4 mean? 2 power 4 entries in each chunk. What does 6 means? 2 power 6 entries in each chunk. What are those 8 means? 2 power 8 entries in each chunk. What about this 12 means? This 2 power 12 entries. In last level, each entry just contain 1 byte, but that is okay. 2 power 12 entries in each chunk. So this should be clear to everyone that what does this number mean. Now let's just talk about number of chunks. Okay. So at top level, the number of chunks always 1. At top level, it is always 1. Number of chunks are always 1 at top level. At this level, whatever the number of entries in the previous chunk, I mean total number of entries, so this is 4, it means 2 power 4 chunks, and then total is 10, so it means 2 power 10 chunks. Total is 18, so it means 2 power 18. So there are 2 power 12 entries, and at the last level it is just a byte. So there are 2 power 12 bytes in each chunk, and total there are 2 power 18 chunks. So if there are total 2 power 18 chunks, each chunk is having 2 power 12 bytes, so it means 2 power 30 bytes I am having in the total process, and which is actually true, right? Because 30 bits is my process size or the virtual address space, right? Okay. Let me know if this particular diagram is clear. That is just one aspect. I will just tell you one more thing. Okay. First, it has to be clear to everyone. Henry, is this clear to you? Okay. The number of chunks and number of entries in each chunk should be clear, right? In each chunk, it is not the total number of entries. If I need to find out the total number of entries, you have to multiply these two numbers, because this is just entry in just one chunk, and then you have to multiply these two to find the total number of entries, right? So you can even find the total number of entries. Okay, that you can find. That is just one aspect. Second thing is that, see, each is right. So I hope you understood this, right? Now let me just tell you one more thing here. See, each is basically, this is having 2 power 4 entries, and each is pointing to one chunk. Each is pointing to one chunk, and each chunk here is having 2 power 6 entries, right? This is 2 power 6 entries. Okay, let me know if that is fine to everyone. This is 2 power 4 entries, and each is pointing to something which is 2 power 6 entries. Let me just convert. Let's suppose the page table entry size is given to you, which is suppose 4 bytes, right? Which is 2 power 2 bytes. Can you convert this number of entries to bytes? This number of entries, if you want to convert to the bytes, it is 2 power 4 into 2 power 2, which is 2 power 6 bytes size, right? Size of the page table here. And similarly, this is 2 power 6 into 2 power 2, which is 2 power 8 bytes, something like this, right? Now, let's suppose your physical address space is of any number of bits. Let's suppose it is 20 bits. Now, what I'm asking is that how many bits you need here to address it? How many bits you need here to address something which is having 2 power 8 entries, which means 2 power 10 bytes, right? Similarly, how many bits you need here to point something which is having 2 power 12 entries, which means 2 power 12 bytes. Here the entries and bytes are same in the last level. Okay. This is the question that we are asking to ourselves. So basically, this is one aspect. You first have to understand number of entries, number of entries in each chunk, number of chunks. Then how many bits I need to address that chunk. That is the second type of question that I in this multi-level paging they can ask. Okay. So I hope both of this is clear. And how to solve this, we have just went about solving it in the previous lectures. Now I mean the previous slides. Now let me just move further, and maybe after the few slides, this kind of calculation will come again. Okay. If you're not much comfortable that how to calculate the number of bits here, okay, to point out these chunks, then it will be clear, because we will be solving other questions. See here what they are saying. Consider a computer system with 40-bit virtual addressing and page table size. If the computer system has one level page table, okay, I think that question can be solved by your own. Okay, so you can solve this question as a homework. Okay, let me go to some question that I want to solve, because these questions can be solved as a homework. Let me go to this question, which is a nice question. A processor uses 36-bit physical address and 32-bit virtual address. Okay, so see, 36 bits physical address has been used. So physical address space is 36 bits, and the virtual address space is given to us is 32 bits. That is fine. I mean, generally it's not the case that virtual address space is lesser, but it is fine, right? Because the virtual memory is basically saying you can store in the hard disk. I mean, that's the main mode of the virtual memory. Each page table entry is of size 4 bytes, right? So page table entry is also given us 4 bytes. A 3-level page table is used for the virtual to physical address translation, where the virtual address is as follows. So they want to use the 3-level page table. So they have to tell the split, right? And they are telling the split. They are saying 3231 is used to index the first level page. So this is 0 to 11 is basically, which means 12 bits, right? So 12 bits is for page offset, and for the remaining 20 they are saying 8 or 9. This 12 to 20 is 9, right? So 12 to 20 this is 9, 21 to 29 this is again 9, right? And then these are 30 and 31, 2 bits. Okay, can you check whether it is 32? 9 and 9, 18 and 20 and 12, yeah, 32. So the address split is given to us. As I said many times, that address split has to be given to you, right? If it is not given, then there must be some hint to calculate it. You cannot guess it, obviously. Okay. Now what they are asking is very simple question. The number of bits required for the addressing the next level page table. In the page table entry of the first, so they are saying this is the first, okay, they are saying this is the first one. I mean, this is not very standard, so they have to tell which is the first, which is the second, which is the third. The second level page, this is the third level. So now they are saying that how many entries do you need here? Do you need here? Okay, so there, can you tell me first number of entries, total number of how many bits you need here? So total number of entries are 2 power 2, which means 4 entries you have. Each is pointing to something, some chunk which is having 2 power 9 entries, right? I told this thing in this particular lecture many times, that what does this address split mean. So this means it is pointing to something which is 2 power 9 entries. Now can you tell me, in number of bytes, can you convert that to number of bytes? You have to just multiply these two things, which means 2 power 9 into 2 power 2, which will be 2 power 11 bytes, right? So it is pointing to something which is having 2 power 11 bytes. Is this clear to everyone? Now similarly, it will point to something which is again 2 power, which is having again 2 power 9 entries. So there's a similar story, which means 2 power 9 entries, which means 2 power 11 bytes, right? Again, this is pointing to something which is having 2 power 12 entries, right? 2 power 12 entries, which is here the entries are just bytes, 2 power 12 bytes. Okay. So I hope this diagram is clear to everyone. How many chunks are there? Many. And many means like this will determine, which means 4 chunks are there. Anyway, like number of chunks are not much important at this question, for this question, but yeah, these are 4 chunks. Here at this level there are 11 chunks. Here at this level these are 11 plus and 2 power 20 chunks. So here at this level 2 power 11 chunks. Here at this level 2 power 20 chunks are there, right? Number of chunks also you can find out. I am just writing one chunk. So this is just one of them, right? This is just one of them. This is just again one of them, right? So there are many chunks. Okay. Now tell me how many bits you need here to point it. Since it is 2 power 11 bytes, the physical address space is 36 bits. You have to divide it like this, 11, and then it will be 24. Sorry, 25, right? Yes. So you need 25 bits here to point here. It is pointing to something that is again having 2 power 11 bytes. Size is 2 power 11 bytes. So again 25 bits here. It is pointing to something which is having 2 power 12 bytes, which means you have to divide like this. 12 and then this will be 24, right? So it will be 20, it will be needing 24 bits, 25 bits, 25 bits, and then 24 bits. So that is why D is the correct answer. Let me know if that is understood, right? So 25, 25 and 24 is the correct answer. See, I told it many times. Let me know if that is not clear, because that's most crucial question that we have in entire multi-level paging. You should be able to understand that what it is pointing to. It is pointing to something which is having 2 power 11 bytes. If it is having 2 power 11 bytes, see, let's suppose I point to something, okay, if I need to point to one integer, okay, let's suppose if I am pointing to one integer of 4 bytes, then what is the number of bits I will be requiring? Let's suppose my physical address space is, suppose again this is 36 bits. If the integer is just requiring 4 bytes and my physical address space is 36 bits, so let's suppose this is a physical address space, then you will say you have divided the physical address space into 444 bytes, something like this. I mean, whatever you want to point to, you will say that you have divided your physical address space into that size. So it will be 36 minus 4, which is 32, which means you need 32 bits to point to one of the integer, right? Why? Because integer is of 4 bytes and your physical address space is 36 bits. So that is why you will be requiring 32 bits to point to one of the integer. Okay. So I hope that is clear to everyone. Now suppose instead of integer, if it is a character, that is just having 1 byte, if it is a character that is just having 1 byte, so you will be requiring 36 bits here. Okay. Similarly, if it is something, let's suppose if it is a page table, okay, if it is a page table that is having, let's suppose 2 power 11 bytes, then since each is having 2 power 11, how many such chunks or such page table are possible or sub pages are possible? This is 2 power 11. You have to divide your physical address space like this, 11, and this is 25. So you need 25 bits here. Okay. I hope it is clear to everyone. It should be clear because it is very important question, right? Okay. I have talked about this question. I mean the all the detail of multi-level paging in the previous slides in today's lecture only. So if you have not understood anything, you can just go back to the first of this minute of this lecture, and you can start the lecture again. You will get to understand. So this is one of the mostly popular question on the gate overflow. If you see, there are many views on this question, so which shows that this is mostly popular question on the gate overflow. And see here, D is the correct answer, right? Okay. Now I want to solve one or two very important questions which has been asked in GATE 2003 and also in GATE 2021. These both are similar questions, but due to the lack of time, I will be solving it tomorrow. Tomorrow I will be solving some more questions of this paging and related to memory management. So today we have mostly focused on the virtual memory, specifically on the paging part, which is multi-level paging. Tomorrow we will be focusing on TLB segmentation and these kind of questions. Okay. So let me know if that is clear. Please comment it out. If there is something that you have not understood, if you have understood everything, please let me know so that I get to know that how the sessions are going, right? Just comment it out that you have understood everything. Okay.